Hi guys, Sajjad Hussain again with a new video. In fact, this is not a new video, rather it is in continuation with my old video. In my last video, I calculated the wind and seismic forces on a 12-story building. I took this building from the example number 29.1, and this is taken from PCA notes 31808. In this example, we considered a 12-story building. Let me show you the elevation of the building. This 12-story building has 11 stories which are 12 feet high as shown here, but the ground floor is not 12, rather this height of the ground floor is 16 feet. And the members are like that. For example, the exterior columns are 24 inch by 24 inch. Interior columns are 30 inch by 30 inch. Beams are 20 by 24 inch deep. All slabs are 8 inch. The walls are 18 inch web plus a 32 by 32 inch boundary element. It is a bit difficult to model this 32 by 32 inch boundary element for the time being. So for the sake of simplicity, what I will do, I will take all walls at 18 inch thick, and the loadings are defined like this. That this example and the 5 examples that follow illustrate the design and detailing requirement for typical members of a 12-story cast-in-place concrete building. Our typical plan and elevation of the structure are shown in figure this 29-26A and B, which I have just shown you. The columns and structure walls have constant cross-section throughout the height of the building, and the bases of the lowest story segment are assumed fixed. The beams and the slab also have the same dimension at all floor levels. Although the member dimension in this example are within the practical range, the structure itself is a hypothetical one and has been chosen mainly for illustrative purposes. Other pertinent design data are as follows. The concrete itself is 4000 psi concrete with its unit weight as 145 pound per cubic feet. Reinforcement as usual, Fy is 60,000 KSI. Service load, live load on the floors are 50 pound per square feet. Additional average value to allow the heavier load on corridor is 25 pound per square feet. So the total average live load comes out to be 75 pound per square feet. The roof has 20 pound per square feet live load. However, the superimposed dead load are given as average for partition is 20 pound per square feet. Ceiling and mechanical are 10 pound per square feet. The average total is 30 pound per square feet by adding these two. But the roof itself has 10 pound per square feet. Seismic data for this building is SDC-D. Dual system, that is a special reinforced concrete structure wall with a special moment frame in north-south direction and a special moment frame in east-west direction. So let me show you again the plan. Here is the plan. This is the north-south direction. In north-south direction, we can see the concrete special frame with shear wall over here on grid number 2 and on grid number 7. These are the two shear walls. But in east-west direction, there is no shear wall. The moment frame, special moment frame system is resisting the lateral load in east-west direction. So with all this information, I will model this structure in Etabs. But before going that, since one information is given over here, that the seismic design data is SDC D only. No other parameters are given. Similarly, no information is given about the wind load. So what I did, I checked these values from ATC data, and I took this information from ATC website. As per the ATC website, as per ASC 705 for seismic category D structure, for SDCD structure, the values are tabulated over here, like SS is equals to 1.5, S1 is equals to 0.678, and all these values, they will be derived. Long period is 12 seconds. So all this information is taken from ATC website for San Francisco, California, and we will be using these values for SDCD. Although this information is not given and the lateral analysis for this building is not given in this example, but we will take this as our standard example. And for the same location, the wind load as per ASC 705, the wind speed is 85 miles per hour. I am not using ASC 710 or ASC 716 to define the wind load. I shall be using ASC 705 to define my wind load. So I shall be using this value 85 miles per hour to define my wind load on this structure. So let us switch to Etabs. In Etab, we will start a new model. Let us start from File, a new model. When we open the new model, when we click the new model, and then there is a window opened, and this is model initialization. There are three options. We can use the saved user their default system, or we can use setting from a model file, or we can use the built-in settings. Let's see, use the built-in setting. Units are US customary, which is okay. Steel section design, we are not doing anything. Steel section code, we are not doing anything. Concrete design code is ACI 31808. So this is perfectly acceptable to us, and we can start from here. Let's click OK. When we click OK, another window opens. This is new model quick template. And this template we can define our building, but there are various options available. For example, we can start with a blank file, or we can define grids only, or we can define a steel deck, or staggered truss, flat slab with perimeter beams, waffle slab, or two-way or rib slab. So the most appropriate template is two-way waffle slab system. Now, here there are various information given. For example, uniform grid spacing, number of grids in X direction. As you might have noticed, in X direction, let me show you the plan. In X direction, there are 1, 2, 3, 4, 5, 6, 7, and 8 grids. All these grids are 26 feet apart. In Y direction, A, B, C, and D, all these 4 grids, they are at 22 feet apart. So let us input these values. Number of grids in X direction, 8. Number of grids in Y direction is 4. Spacing in X direction is 26 feet. Spacing in Y direction is 22 feet. Let's confirm. Yes, 26, 22. Correct. Now, story data. Number of stories are 12. Typical story height is 12, but the bottom story is 16. So all these informations are given over here. Now we can click two-way or ribbed slab system. When we click this two-way ribbed slab system, another window opens, which is the structural geometry and property for two-way or ribbed slab. The first section is overhangs in ribbed slab, and here is a check button whether these are ribbed or no. No, these are not ribbed. So we will delete or we will clear this check button. Now overhangs along X direction and along Y direction. If we go back to our model, let's see. All the exterior columns are 24 inch by 24 inch. So that means this overhang will be 12 inch here, 12 inch here, and all directions the overhang will be 12 inch or 1 feet. So we can input this value over here. Overhang 1 feet in left, right, top, bottom. So all our overhangs are 1 feet. The bottom is fixed as already defined in the model. Now, these are some column sections, but we do not know what these sections are. So we have to see what these sections are, and if needed, we will modify this section. For example, this structural system properties column. Let's go to the column first. Concrete column. What is this concrete column? We will see concrete column. So we will select this show or modify or show the properties. When this concrete column we see the material is 4000 psi. Let us click the material 4000 psi, show or modify. So when we see over here the material data, the material name is 4000 psi concrete. We are not going to change. Material type is concrete, isotropic, everything is okay. Specific weight density is not 150 as per the problem, it is 145. So we will click OK. We will click OK. This section is a concrete rectangular section. Now the section dimensions, let us assume that these are all exterior columns which are 24 inch by 24 inch, and we can see here that these columns are exterior columns. So let us put extension of EXT, that means exterior column. So now we are defining exterior columns. The property modifier, is there any property modifier? For the time being, we are not going to change the property modifier. We can change in the design stage also. Reinforcement, okay, let us see the reinforcement. This is P, M2 and M3 design for column, that is correct. All bars are 615 grade 60. Ties are also a 615 grade 60. Material is correct. This column configuration is rectangular with confinement. Bars are tie bars, and all the reinforcement are to be designed. These covers, we are not going to change anything over here. Let it be on default value. Longitudinal bars number 9 we will leave as it is. Confinement bars, that is the tie bars, we will leave as it is. Okay, so that is correct. Okay, so the columns are selected as exterior columns. Later on we will change the interior columns, but for the time being all columns are exterior columns. Then beam in X direction, we know that all the beams are 20 by 24. So let us modify concrete beam. Since there is only one section, so no need to put any extension or further addition of that. Concrete is 4000 psi. As we know that the beams, concrete beam is 20 by 24 inch deep. Let us see, depth is 24 correct, but width is not 18, rather 20. Any modifications for the stiffness? No, we are not going to do anything. Let's see the reinforcement. It will be a beam design, and rest, the cover, etc., steel, they are all on default. We are not going to change anything over here. So we have defined concrete beam in both the direction the same. Now comes the slab. So let us take this slab and let us see what type of slab this is. Slab thickness is 8 inch. As you know, we have seen that in the example the slab thickness is also 8 inch. So we will leave as it is. We will leave these values untouched. Okay. So far our section properties are defined over here. Now the load. In dead load, is there any additional dead load? Yes, there is additional dead load. So what we will do, since we cannot segregate for the roof load and other floor load here, so total floor load for the dead load is 30 pound per square feet. Later on we will modify, and the live load is 75 pound per square feet. As we saw before, let us confirm once more. Live load is 75, superimposed dead is 30. So we just correctly input these values. Additional dead load is 30, live load is 75. The floor diaphragm rigidity, it is rigid. So now we have checked all these parameters and we have modified wherever the modification were necessary. So let us click OK. Let us click OK. And here is the structure modeled. Now you can see there are 3 windows, 1, 2 and 3. This window is a 3D view. This is plan. Here you can see the plan view at story 12, which is at a height of 148 feet. If we go down, you can see the stories are changed. Now this is 11th story at 136. Further go down, 124, 10th story. So for 9th story, if we go once more, 8th story and so on. So let it be at 12th story. So we are at the top, roof level. And here is the model explorer. Here you can see model, display, tables, reports and detailing. As we will develop our model, so these pages will be populated and we will go into details. But for the time being, let us see what is over there. So the project information, if we want to give any information over here, we can give the information over here. For example, the client name. So we can say XYZ Private Limited. Project name, we can say high-rise flats, whatever. The project number, we can say this is our first project. We can write the name of the company over here. We can say A, B, C, D consultants. Engineer logo, we don't want to have any logo over here. Otherwise we can import some figure or some picture. I don't have at present anything over here, so let's delete this one. Engineer MSH is myself, Muhammad Sajjad Hussain. Checker, public, supervisor, public. More information, model name, we can say, we will save this as example 29-1, and since we are doing this in 2020, I think it's more than enough. Okay, so let us save this file. Save as. Example 29.1 2020. Save. So far we have saved the geometry and loading, but we know that we have to modify the loads anyway. Then another important factor is now we have to define the wind and seismic forces. So what we have to define? We have to define the load pattern. We know that there are only two load pattern defined, that is the dead load and live load. So what we have to do, we have to define the wind load. We will define this wind load as per AC 705. AC 705, here it is. And let us modify the load now. Sorry. Cancel. Define load pattern. We have to add the wind load. I did a mistake. Wind AC 705, add new load. Now we have to modify this lateral load. In this lateral load we have to define exposure from extent of diaphragm. We have not yet defined diaphragm, we will define the diaphragm later on. And user defined or program defined, let it be program defined. All the created, so this Etabs will create all the load cases as per figure 6.9. That means all these load cases will be defined like that. There are 12 load cases. We will generate to define, we will select to define all these possible wind load cases. Wind speed is 85, exposure is C, importance factor 1, topographic factor KZT is 1, gust is 85, rest is same, and the top story is 12, bottom story is okay. We are not considering any parapet over here because no parapet is defined in this example. Otherwise we can select over here and we can define the height of the parapet over here. So let us delete this option. Okay, so now we have defined the wind load, and now we are going to define the seismic load. That means earthquake in x direction. So it will be seismic, and it will be as ASC, as per ASC 705. Add. Similarly, we will define y as per ASC 705. Now we have to modify ASC 705 wind load case in x direction. Let us modify the wind load, the seismic load. So first we are going to modify this seismic load in x direction. So we will delete y direction from here. Eccentricity, that is correct. Now we have to take some help from my previous calculation. Like last time I showed you that to define my model, I have to define all the load cases over here. So what I did, I calculated the seismic and wind load cases in MathCAD, and let me show you what I have done. These are all right up. The wind load is okay. This is gone. Seismic load case. SS is 1.5, S1 was 0.678. So let us use these values. But here, to calculate the time period, we have to select which formula should be used, especially in x direction. X direction means in east-west direction. So all these values are here. Let me select the correct zoom. So in east-west direction I did not use, but I calculated. So in east-west direction, our parameters should be (0.2 and 0.75). Okay, and in east-west direction our parameters were R should be 3, omega should be 3, CD just one moment please. In north-south direction we took this value, and in east-west direction as you can see over here the R was 8, omega was 3 and CD was 5.5, 8, 3, 5.5 and 1. The value of SS is 1.5, S1 is 0.678, long period was 12, side class was D and rest is correct. Okay. Similarly, we can define in Y direction, which is north-south direction. So we will click these ones to clear X direction. We will remain Y direction will remain checked, and here and same thing. This will be 7, rest is okay. SS is 1.5, S1 is 0.678, long period is 12, side class D. Okay. So these are the seismic loads defined. Let us see the load cases. These load cases are there. Now let us define the diaphragm. There is only one diaphragm. Okay, so we have to assign this diaphragm. Select object type, floors, and we will assign shell diaphragm. There is only one. So let's see, if we go down, all are defined like diaphragms. So let us save the model. Now, before further proceeding or definition of load combination and changes in the forces or internal column definition, etc., let us run one time and let us see if we can analyze it or no. Now we can see that deformed shape here. This is for displacement in case of dead load. We can display deformed shape for live load also. This is the deformed shape for live load. Now for wind, we can apply for the first load case. Wind in X direction, we can animate. Okay, so this is wind in X direction. Let us stop. Let's go to second mode, apply. Let us start the animation. So this is the wind direction, this is the deflection in Y direction. This is the second case for the wind. Similarly, we can check for the earthquake loads. Earthquake in X direction. Let us apply. So let's see the animation. So this is the wind load case in X direction. Let us see the other wind load case, the seismic load in X direction. Let us see the seismic load in Y direction. Now you will see the deflection in Y direction because of the seismic load. Seismic load in Y direction, that is perfectly fine. Okay. So let us stop for the time being now and wait for my second video. This is the first video for this modeling. In the second video, I'll show you how to change the loads in service live load and superimposed dead load, and then the load combination, design, detailing, etc. So for the time being, let us stop over here.